Inside your smartphone right now, there's a piece of polished silicon no larger than your fingernail. Carved into this tiny black square are over 15 billion microscopic electronic switches called transistors. If you wanted to see a single one of these switches with your naked eye, you would have to shrink down to the size of a single strand of human DNA. These microscopic gates flick on and off billions of times every second to power your apps, process your photos, and calculate artificial intelligence queries. Yet here is the most staggering secret in modern engineering. Every single advanced microchip on Earth, from Apple and Nvidia to supercomputers and satellites, is manufactured using one single machine built by one single company in the Netherlands called ASML. This machine costs over $350 million, weighs 200 tons, requires 3 Boeing 747 cargo planes just to ship, and fires high-powered lasers at molten metal 50,000 times every single second. To understand why this colossal machine is considered a modern miracle of physics, we first need to see how microchips are actually printed. Microchip manufacturing is essentially ultra-precise stencil photography. Engineers shine a bright light through a giant glass stencil called a mask, which contains the blueprint of the circuit. A system of optical lenses shrinks that image down and projects it onto a silicon wafer coated with light-sensitive chemicals, etching billions of microscopic paths. For decades, this optical method worked brilliantly. Engineers used deep ultraviolet light with a wavelength of 193 nanometers to carve smaller and smaller circuits year after year. However, as transistors shrank below 20 nanometers, chip makers hit a hard brick wall of physical optics. The light wave itself was simply too fat. Imagine trying to draw a fine portrait using a giant, fluffy house painting brush. Because the 193 nanometer light waves were wider than the tiny features they were trying to print, the light began to bend, scatter, and blur around the edges. Visible physics had run out of room. To shrink transistors down to 5, 3, and 2 nanometers, engineers needed an unimaginably sharp light needle. They needed extreme ultraviolet light, or EUV, with a razor-thin wavelength of just 13.5 nanometers. There was only one massive problem. EUV light has a bizarre and destructive physical property. It does not exist naturally in Earth's atmosphere, and it is instantly absorbed by literally everything. If you shine EUV light through a standard glass camera lens, the glass swallows it completely. If you shine EUV light through normal room air, the floating oxygen and nitrogen molecules absorb it like a black hole. To use this ghost light, ASML had to build a machine that operates in a total cosmic vacuum and invent a terrifyingly violent way to manufacture light out of pure chaos. Inside the light generator, a high-pressure nozzle squirts droplets of molten tin, each one 1/3 the thickness of a human hair, into a vacuum chamber at 200 miles per hour. As each microscopic droplet falls through the dark chamber, a massive industrial carbon dioxide laser fires a double pulse. The first laser pulse strikes the falling tin droplet, instantly flattening it into a microscopic pancake. Microseconds later, while the droplet is still falling at high speed, a second immensely powerful laser pulse obliterates the tin pancake. This violent impact vaporizes the metal into a blazing ball of plasma heated to 400,000 degrees Celsius, hotter than the surface of the sun. For a split microsecond, this miniature star emits a blinding flash of pure 13.5 nanometer EUV light. And this precision laser explosion happens 50,000 times every single second, nonstop, day and night. Since normal glass lenses absorb EUV light, the light cannot be focused using standard optics. Instead, it must be guided and reflected using a sequence of ultra-custom mirrors crafted by the German optics giant Carl Zeiss. These mirrors are polished to atomic perfection and coated with over 100 alternating microscopic layers of molybdenum and silicon. They are officially the smoothest and flattest artificial surfaces ever created by humanity. To put their precision into perspective, if one of these Zeiss mirrors were expanded to the size of the entire country of Germany, its highest microscopic bump would be less than a single millimeter tall. If a mirror were rougher by anything more than the width of a few atoms, the EUV beam would distort, destroying a silicon wafer worth tens of thousands of dollars. Once the EUV light bounces through the flawless mirrors and passes through the circuit stencil, it focuses down to a 12-inch silicon wafer. At this scale, human footsteps or distant traffic vibrations would ruin the alignment, so the silicon wafer rests on a frictionless magnetic levitation stage that glides through the vacuum. This robotic stage accelerates, repositions, and stops at 10 Gs of force, faster than a supersonic fighter jet catapulting off an aircraft carrier. It aligns the wafer beneath the pulsing EUV light with an accuracy under a single nanometer, the width of just 4 silicon atoms. In a matter of seconds, an entire grid of microprocessors containing trillions of interconnected transistors is permanently carved into the silicon. Today, ASML's high-NA EUV lithography machines represent the most critical technological choke point on planet Earth. Every frontier artificial intelligence model, autonomous vehicle sensor, and smartphone superchip depends entirely on this single machine. It took 30 years, tens of billions of dollars, and the collaborative genius of thousands of scientists across dozens of nations to bend the laws of physics. So the next time you unlock your phone or interact with an AI model, just remember, you're holding the power of a machine that shoots lasers at molten metal in a vacuum just to shape light at an atomic scale.